Hello Internet, my name is Quinn and this is Blondihacks. Yes, I'm still working on the cylinder drain valve control mechanism for my Pennsylvania A3 switcher locomotive. We've got more parts to make still. This is a very complicated system, so let's go. Closing in on our goal now of fully functional controllable drain valves. We've got the basics working underneath the cylinders as you saw previously in this series. I want to move to the other end of the assembly now, specifically the control lever and associated mounting bracket up in the cab. These two pieces are both quite interesting, and they're going to make up a video all by themselves, and you'll see why as we get into this. There's quite a bit to them. That control lever has a bell crank built into it, which controls the reach rod and forms the first directional change that the linkages need to make. And this lever moves up and down, as you can see open and close marked in the drawing. It's quite a nice design. Close is the down position so that as the locomotive is underway, any vibration or anything won't cause those valves to kind of drift open on their own from the weight of the lever. If there's any looseness, it's going to default to closed, which is what you want. I'm going to start with the triangular bracket that holds this lever, and I thought, I was sure in fact, that I had a piece of bar stock the perfect size to make this, so I didn't order anything. And well, turns out I actually don't. I came up a little bit short on this piece that I had earmarked for this part. It's 31 thousandths too narrow on one dimension, so I need to decide what to do about this. I could try and silver solder a couple of pieces together, and that would work, but there'd be a weird seam in the part somewhere, and I'd have to decide where to put that seam. There really isn't a good place for a join like that. I also can't mess with the distance between the hole and this curved slot. That's a very critical dimension. I also can't mess with the width of the mounting holes because those are already set in the footboards. So really I'm looking at changing the dimensions of the part, and I'm looking for a way to do it in a harmless way. And looking at the overall assembly, it seems like I'm okay to shorten the part a little bit. This will allow me to maintain all the internal dimensional relationships that are so critical. The only thing that's going to be affected is potentially the travel angle of the reach rod that connects to the top of this lever. However, that rod is over a foot long, so we're only talking about a couple of arc seconds of change in the travel of that lever, and so it's really not going to affect anything to make this bracket a little shorter, and if it is a problem, I can always add a little packer block later on. So that's what I decided to do. And let's get started over on the bandsaw by lopping off a chunk of this with which to make this part. As is becoming tradition around here, I'm going to start by squaring it up and bringing it to dimension on the shaper. Still the most fun way to do this. The shaper is actually very quick and efficient for these kinds of edge cleaning up type operations because it's already set up, it's already sitting there. I never have to change any tools, I never have to mess with moving heads up and down and collets and all the rest of it. The machine is just sitting here already ready to do this type of job. Whenever I change a dimension on a part like this, I always note it in the drawings so that later on, if I'm doing some math on a part or I need to reference something else in the assembly, I know that I've changed that dimension because that could obviously cause problems later on. Now I'm going to drill and tap the mounting holes for the bracket first. That's easy to do while the part is still square. Next, I'll do a bunch of edge finding because I need to locate the position of the hole, which is a critical reference for the curved slot feature that will be coming next. So, taking lots of care here because all of these dimensional relationships now become quite important. That's the easy stuff, but now it's over to the rotary table to cut that curved blind slot. Everything about this is critical. It needs to have the exact right arc length, it needs to be the exact correct radius from the center of that hole, and the arc has to be centered on the y-axis of the part. As a result of all that, the centering of this part on the rotary table is really critical, so I'm verifying it by rotating the table in 90-degree increments and comparing, making sure that the gauge pin still goes in the hole without touching it or without deflecting at all. If the concentricity of this reference hole is off, then all hope is lost as far as getting this curved slot correct. I might as well give up and take up woodworking at that point. Once concentricity is established, I need to get the y-axis of the part aligned with a 0 on the rotary table. Now this is a little bit tricky. There's a couple of different ways to do it. You can indicate in some sort of fence on the rotary table, which I don't actually have set up on this rotary table, so I don't have an easy way to do that. Another way to do it, though, that's just as quick for one-off parts like this is to clamp a parallel to the reference side of the part and then feed it in and out with an indicator and rotate the table until that indicator is zeroed out. And that gives you an offset on your rotary table that you just need to add to all of your angle measurements, because you can't zero a rotary table, or at least not this one. Maybe there's some fancy ones that you can. And as I said, you can set up a fence, but you have to dial in that fence anyway, so you might as well just dial in the part if you're only doing it once. Then I rotate to my starting angle, taking care to go past the starting angle and coming back in the direction of cut to eliminate backlash in the rotary table. And now I'm ready to cut. I'm using a center cutting end mill so I can plunge down to the final depth. This is a blind slot and it's not very deep, so I can do this in one cut. Once I'm plunged down, I lock my spindle and start my rotation. Of course, I calculated my stop angle ahead of time, accounting for the little offset for zeroing the table, and I'm watching my scales like a hawk to come up with that stopping point. Once I'm there, I lift out of the cut, and we're done. This is one of those features where the setup takes 5 times longer than the actual cut does, but it has to be right, so take the time to do it. Now that's a little bit tight. I did a test with a gauge pin there, so I did a couple of skim cuts, pushing the table just a few tenths forward and back, and ran those cuts again, and now that's moving very smoothly in there. There's going to be a pin riding in that slot, so I want it to be a nice sliding fit on the nominal dimension. Well, with the hardest part out of the way, now let's get to the final outer shape of this part. Got a gauge pin in the hole for reference, so I can find that on the surface plate, and then I'll mark the tangent points around that hole so that I can connect the triangular sides to it. With those tangent points marked, I can take our happy little Cyclops over to the bench and connect the dots. The outer corners of the stock are the other ends of those angled cuts, and well, this is where we need to stop and talk about math a little bit, because this basic approach that I usually use is not going to work here. You can see why. If I now connect circle around the tops of those tangent points, we're not going to end up with nice flowing lines on the sides of the part. We're going to end up with a little domed hat on the top of our Cyclops. And that's not what we want. And the reason this doesn't work is because, of course, these 90-degree tangent points on the circle are just approximations. They're correct if the sides are 180 degrees, but the further from 180 you get, the less accurate those actually are relative to the true tangent points of the circle. Using those 90-degree points is a nice shortcut because that's super easy to mark out on the surface plate, and it works most of the time on most parts. But the closer you get to 90 degrees, the less accurate that gets, and especially once you become obtuse, then I start removing your comments. But more importantly, then these tangent points really move above center line quite a bit on the circle, and it starts to look funny, as you see here. You can, of course, use some junior high school math to calculate where the correct tangent points should be for given included angles around the circle. However, there's an easier way. I happen to already have a filing button the correct dimensions for a feature like this, so I'm going to stick that filing button in there and trace my circle. And this allows me to determine geometrically where the tangent points are instead of mathematically. With that circle on there, I can now connect the dots with the outermost point of the circle that a straight edge will touch along with the other end of the edge that I want. And hey, don't feel bad for not wanting to do the math. Machine shop work is very much about eliminating sources of error, and math is a big source of error, right? I have a post-secondary computer science education, but I have scrapped parts by screwing up arithmetic that a 5-year-old can do. A mistake like that doesn't make you stupid, it just makes you human. There's no trophies in the machine shop for doing something the most sophisticated or fanciest way. If there's a way to eliminate the math without substantially compromising the part, which is the case here because we're creating cosmetic features only, then you should do it. Luckily with DICAM, it's easy to start over. I'll erase my bad lines there. And I've traced the circle and connected the tangents geometrically, and look how happy our little Cyclops is about that. And trust me, you do not want an unhappy Cyclops in your house. That gets mythological real fast. Over to the milling machine then to remove that material down to that layout line, using my favorite technique for this, which I've explained a zillion times with the parallel trick. Now normally if you've watched this channel, you know I would go over to the bandsaw to remove the bulk of that material because there's quite a lot here to turn into chips. But I'm not doing that in this specific case, and I think you'll find the reason really interesting. You see, because in this specific setup on this particular part, because shut up, that's why. Starting to look like a part now. All that's left is to round the top corner of that, and the perfect tool for this situation is my little belt sanding fixture. Swing that around a few times and Bob's your uncle. This was actually quite an interesting part to make. That curved slot feature was quite tricky to get right, but as you'll see on final assembly, I think we nailed it. On now to the lever that rides on this bracket. This is a very interesting part. You can see that it's a bell crank with a clevis at the small end and the control lever handle built right into it. Now that control handle could be done as a separate part and attached, but I think it's actually going to be easier and stronger to machine this all out of one piece. I'm going to see how I do that. This is usually the part where I have to make a piece of metric bar stock out of whatever I have, but shockingly, in this one instance, somehow, I have a piece of 5mm hot rolled plate in my bin. I don't know where this came from or why I never found it before, but here it is, and it's going to save me a bunch of work. So I'll rough cut a chunk of this out on the bandsaw, a little bit larger than the overall part, and that'll get us on our way to this bell crank lever thingamajig. Don't look at me, that's the technical name for it. Blame the Victorians. Now, starting with whichever saw cut looks the straightest on the shaper, I'm going to create some parallel edges all the way around it. For reference, I'm going to create one edge on this stock that's parallel to the long axis of the lever. It's going to be a really helpful reference for the handle and that big hole and so forth. Once I've got a reference edge, I can take it to the surface plate and lay out the handle area and the L-shaped bell crank area, which are going to be done separately. Here you can see I've marked the center line of the handle and the outer boundaries of that handle. And I'm going to rough cut out this shape on the bandsaw to start with. Next, perhaps counterintuitively, I'm going to machine those saw cuts even though these surfaces are temporary. And that's because these saw cuts being parallel and on dimension correctly centered on that scribe line are going to enable me to set this up in the lathe to turn that control handle. I've got my forward jaw set up with a lot of offsets so that I can get the handle area that we've just machined centered on the spindle of the lathe. I'm going to do that by dialing it in as a rectangular piece of stock. I actually have a video on how to do this if you're interested, but suffice to say you dial in opposite sides of the part by finding the lowest reading on each surface. That tells you when that surface is vertical, and you dial it in 180 degrees across the part each way. Because the part might not be perfectly square, you may have a different indicator reading on each axis of the part. An easier way to do this, if you can, is to put a center punch in the center of the feature that you want to align with the spindle, and I've shown how to align a center punch on the lathe before. However, for this part, I don't want a center in the end of this feature. And away we go. That rectangular blank that will become the handle is running concentrically, so I can start turning it down to the largest diameter of the decorative handle. You may recall, if you've been watching this series, that I made a similar handle for the reversing lever, or Johnson bar, as the Americans would call it, as I've recently learned. And on that handle, the dimensions were slightly different, but I want this one to look similar. I want it to kind of look like it's in the same family of levers, like it was made by the same company for the same machine. So as I get started turning the shape into it, you'll see me comparing it a lot with the previous one that I did to create the same aesthetic, as it were. It doesn't actually matter what the exact shape of these handles is, it just needs to look like they both belong on the same machine. And as I said, it's a little tricky because the dimensions of them are different. This valve control lever is a little bit thinner and a little bit shorter than the Johnson bar handle is. But as long as we can eyeball it and make them look aesthetically comparable, we'll be in good shape. And similar to that first lever that I did, I'm doing this with a combination of etch-a-sketching in the rough shape of the handle, and I'm refining it with filing and sanding and going back and forth, iterating on it a little bit at a time, just trying to sneak up on the desired shape. Once I'm happy with that shape, then I switch to emery and I work my way up through 320 and 600 grit to give that a really nice finish. It's not just for appearance, a really good finish on a hand control like this that is mild steel is also corrosion protection. I won't claim it's perfect, but I'm pretty happy with that. Looks like they both belong to the same locomotive at least. That was a pretty interesting lathe setup. I actually enjoyed that, but we're done with the lathe for now, and we can go over to the milling machine and create the rest of the features. Amusingly, the drawing has located the internal features from the end of the rounded handle, so I can line that up with a parallel on the edge of the vice jaw, and then I can edge find on the vice jaw from here. I mean, the relationship between the handle and these holes doesn't matter all that much. The critical dimension is the distance between the two holes on the bell crank area. Conveniently, the angle of this bell crank is 90 degrees, so I can use a square set of references, which is the sides of my stock, to align these holes and get them the right distance from the handle. That's looking good so far. Now to the layout bench for creating the outline of this lever to create the aesthetic shape of it. Once again, doing this geometrically by tracing some filing buttons and connecting the dots with my straight edge. There's the overall shape that we need to create now. It's starting to look like the drawing anyway. It's usually a good sign. I'm going to rough cut that in on the bandsaw. And before I go any further, however, I'm going to cut that little slot at the top to create the clevis at the small end of the bell crank. I've kept one machined surface as a reference for this shaper setup because this slot is parallel to the long axis of the bell crank. That makes an easy setup then. This is a setup you've seen lots before. Recently, I've been grooving a lot of tiny clevises on tiny lift arms and bell cranks because all of these mechanisms in this area use a similar set of features, which is good for me because I ground this tool way back when I did the first one of these, and I've used it about a dozen times since then. It's actually kind of nice to have all of the tooling already set up when you come to make a feature, because then it's super quick. Per usual, I deburr the hole with a reamer. Then I use a pair of gauge pins to monitor my progress on depth using the hole as my reference. Also per usual, the shaper did a bang-up job on what could be a tricky feature. Love that. Now to finish the rest of the outer shape of this lever, which would be nice to do on the shaper, unfortunately I need to stick it down in the vise like this for this cut, and the vise I have on the shaper is very small. Now there's other ways I could set this up on the shaper. It has a box table, for example, so I could mount it vertically on the edge of the table, things like that. And if this was 1965 and I didn't have a very nice Taiwanese milling machine, then that is how I would have to do it. However, I do have a very nice Taiwanese milling machine because it's 2025 and, well, horses for courses. I did a little bit of filing to blend those surfaces into a nice interior corner. And then to round the outside corner of the bell crank, that was a perfect job for the belt sanding fixture. Then to round the small end, I ended up just freehanding this with a file and a little bit of work on the die filer. It wasn't worth turning up filing buttons or any other shenanigans. Honestly, you're never even going to see this end of the bell crank. It's going to be under the footboards, but might as well make it as nice as we can anyway, and it's good filing practice. That's the final lever. I'm very pleased with that. Let's get this installed on the locomotive so you can kind of see how it's going to work. Happy Cyclops gets installed upside down under the footboard in the cab, but not to worry, they enjoy that. Off camera, I made this little T-pin which retains the reach rod and also rides in that curved slot. Then I also made the pivot pin off camera. It's a straightforward turning job with some E-clip grooves. The lever goes on there like that. You can see how that T-pin rides in the slot and limits travel. Very, very nice. That is so satisfying. I actually really love this mechanism. It's one of my favorite of Kozo's designs on this locomotive. Very nice, very satisfying. Well, there's our bell crank control lever for the drain valves. We've made excellent progress now. The end of this entire subsystem is in sight. But thanks so much for watching. That's all the time I have this week, and I will see you next week. And thanks to my patrons for making it all happen.